Hi everyone, and welcome to our webinar, OpenSearch Cost Optimization, Unlock Hidden Savings. I'm Maya Avitan, Director of Marketing at Big Data Boutique, and I'll be your moderator for today's event. A big thank you to our partners at DoIt and AWS for making this webinar possible. We have a really exciting hour planned, during which you'll learn actionable strategies to cut your OpenSearch costs, optimize your queries, and get expert insights from seasoned professionals. Just a quick note, I know you're all really excited about the Q&A section, so we'll be taking Q&A for all three speakers at the end of the three presentations. You can easily submit your questions through the talks using the Q&A section on Zoom. Just make sure to add your Q&A there, and also please specify which speaker your question is for, and we'll address your questions at the end. So first up, we have Mor Aish, who's a partner solutions architect at AWS, who will dive into AWS-specific cost reduction options for OpenSearch. Mor, take it away.
Thank you, Maya. Let me just share my screen. Can you see my screen okay? All right. So hi, everyone, and thank you for joining. My name is Mor Aish, and I'm a solutions architect here at AWS. And today I'll be talking to you about Amazon OpenSearch service cost optimization. So the OpenSearch project started off as a fork of Elasticsearch version 7.10 almost 3 years ago, and had over 500 million downloads ever since, which positioned it amongst the top four search engines currently in the market, with over 70 different partners and contributors developing hundreds of new features ever since. OpenSearch comes in two flavors. The first one is the self-managed. You can simply download the code and deploy it in your systems and manage all the infrastructure and everything yourself. Or the fully managed service, the Amazon OpenSearch service, which I'll be talking about today. So in order to understand how to save costs, we first need to understand the cost model. So the Amazon OpenSearch service cost model is comprised of three main pillars. The first one is compute. For the compute pillar, you choose your EC2 instances and you pay by the hour according to your choice. The second pillar is the storage. Here you have two different options. It's either EBS, Elastic Block Storage, or S3. And again, you pay only for what you use. The third pillar is the data transfer. Sorry. Now this one is important. Since Amazon OpenSearch service is a managed service, you only pay for data transfer in and out of OpenSearch and not between different AZs. In fact, this is so cost efficient that it actually managed to tip the scales towards the managed version for one of our customers who made the decision to migrate from self-managed OpenSearch into Amazon OpenSearch service and deploy a multi-AZ cluster without paying extra data transfer costs for inter-AZ transfer. So the compute pillar is the largest in cost, obviously, but it drives by the amount of storage you have, because the more data you have, the more compute power you need in order to efficiently index and query it. Now let's start saving. So we'll start with the compute pillar. The easiest way to start saving is simply by making a commitment. For steady and predictable workloads, you can use reserved instances or RIs, and simply by signing up for 1 year or 3 year commitment, you can save from 30 up to 50% of your costs. The second option for saving in compute is using Graviton. So for those of you who don't know, Graviton is an ARM-based processor developed here at AWS, and it offers you 38% improvement in indexing throughput, 50% latency reduction in indexing, and 40% improvement in query performance. And all in all, 44% better price performance compared to the previous generation of Graviton processors. It's important to know that since Amazon OpenSearch is a managed service, moving to Graviton is as simple as a configuration change. Since we at Amazon manage all the underlying infrastructure for you, when you choose an EC2 instance of type Graviton instead of x86, the change itself is basically transparent to you. You don't need to manage anything in the move just to pick your processor. Now let's move to the storage tier. So Amazon OpenSearch service data nodes require low latency and high throughput storage in order to provide you with the capability of fast indexing and query. By using the GP3 volumes, you essentially get twice the most storage for almost 10% less the cost. And you can also provision your IOPS independent of your storage capacity, which means that if you need extra IOPS to increase your throughput, you don't need to have more storage just like you did before with GP2. All in all, using GP3 over GP2 can save your costs from 25 to 30% more. And the migration is, again, just a configuration change because you're using a managed service. Another way to save costs with storage is using tiered storage or lifecycle management. So the first tiering storage is the hot tier. This is the default tier. Every information or every data that is ingested into Amazon OpenSearch service by default goes to this layer. In this layer, you have compute nodes backed by EBS storage, and it's the most performant tier of all, and also the highest in price. For less frequently queried data, we have the ultra warm layer or tier. This tier is comprised of compute nodes that are backed by Amazon S3 storage, which gives us 90% less cost and 11 nines of durability of S3, but the latency is a little bit higher, and also the data is immutable, which means you cannot make any changes on the indices once you are in the ultra warm layer. Again, a good use case for this is less frequently queried data. The last tier is the cold storage. Here, the storage is completely detached from the compute, which means you cannot run any searches on your data. And this is mostly suitable for use cases where you have a regulation requirement to save the data for a certain amount of time, but you don't necessarily need to be able to search it. It's important to know that moving between the tiers can be done using a simple API call or even the dashboard's UI. So in case you do need to suddenly query a cold data, you can simply invoke a simple API call and be able to search it within seconds. Now let's put it all together. So the data ingested into OpenSearch goes into the hot tier by default, as we said. Now let's say that after 7 days, we no longer need to query it as frequently as always. So after 7 days, we can move the older data into the ultra warm storage for, let's say, a period of 2 months, after which it can go to the cold storage because we have a regulation compliance requirement to save it for another year. After that year, we no longer need that data at all, so we can just simply delete it. We can automate this entire process using the index state management or ISM tool and have it done automatically for each and every index or cluster that we manage. So just to get a sense of the savings, let's see a real customer example. So for this customer, they had to ingest 110 gigabytes per day and have a retention period of 60 days. So originally, they put everything in the hot tier. So in order to support that, they needed 17 different data nodes and 17 terabytes of elastic block storage, which came down to almost $5,000 per month. After doing some cost savings, they managed to get to 7 days of hot storage only, and then spend the rest of the retention period in ultra warm. This required only 3 data nodes and 4 ultra warm nodes, and got us to just under $2,000, which led us to 62% savings. Now, some of you might say, how come we got from 17 different nodes to 7 in total and still support the same amount of data? Well, there are two reasons for that. The first one is that since we only spend 7 days in hot tier, we don't need as much compute or as much storage, because the less data we have, the less compute power we need in order to be able to index and query it efficiently. The second reason is that ultra-warm nodes are backed by S3, which means we have 11 nines of durability, and we no longer need to create replicas for backup purposes. So we save on that as well. And now for the latest innovation, fresh out of reInvent, is the OR1 optimized instance family. This instance family allows us to get 80% indexing throughput improvement, 30% price performance improvement, and 11 nines of durability, and automatic recovery from red indices. So how does it work? Well, up until now, all the data ingested into OpenSearch was indexed in the main replica, and then copied into the other replicas and indexed again in each and every one of the replicas. With OR1, it works a bit differently. The information ingested into OpenSearch is indexed in the primary replica and then saved into S3, which gives us the 11 nines of durability. But it's saved when it's already indexed, and then copied to the other replicas indexed. So there is no need for extra indexing. This gives us the savings in the compute power, because we only index the information once, and also get us the 11 nines of durability of S3, which means we no longer need to have backup replicas as before. It's important to know that all the features I've just talked about are available by default simply by choosing the OR1 family, but it's only available when creating a new cluster. So you cannot migrate an existing cluster into OR1 instances. Finally, to wrap up, I'll finish with the most basic but sometimes forgotten recommendation. Send only what you plan to search. So Amazon OpenSearch service is a search engine. Our recommendation for best practices is to use it in tandem with a system of records system on the side. Let's say an RDS instance, where all the data will be saved, and use OpenSearch service only to query what you need to, only to index what you plan to query on. And if you need extra data afterwards, you can retrieve it from your SOR. Thank you, everyone, for listening. And Maya, back to you.
Amazing. Thank you, Mor. Now let's turn to Itamar Sinhershko, who's the CTO of Big Data Boutique and a world-class OpenSearch expert. Itamar, I know everyone's eager to learn those query optimization secrets. The floor is yours.
Thank you, Maya. Thank you, Mor, for your presentation as well. And thank you both Maya and Kate and Mor for joining us today. Great to be in partnership with you. I'm Itamar. I'm the CTO and founder of Big Data Boutique. We've been doing OpenSearch and Elasticsearch since basically the days they were conceived, so over 14 years now. And happy to hop on this webinar and kind of walk you through various cost optimizations techniques. I chose to focus on query optimization. And the reason is because it's sometimes forgotten, but to be honest, query optimization is probably one of the most interesting topics in general. And it's also a very strong topic when it comes to cost optimizations, because if your queries are running fine and you're happy with performance, then you're probably oversized and you can start doing some right sizing to optimize your performance. So to optimize your cost, to reduce down cost significantly. And then if you're not happy with performance, the obvious choice would be to throw more hardware on the problem, but maybe that's not the right choice. So optimizing queries is something that you should definitely look into. And in this session of mine here, I'll walk you through a couple of pro tips on how to do that, including some actionable advice. So quickly about us, we are world-class big data experts. We are advanced consulting partner with AWS, and we've been doing, like I mentioned, OpenSearch and Elasticsearch for many, many years now. Me and the team are doing migrations and optimizations pretty much on a daily basis, obviously including the latest advancements on RAGs and Gen AI and so on. We deal with other technologies as well. So even Trino and Flink and Spark and Kafka and others. But like I mentioned, our bread and butter really is OpenSearch and Elasticsearch, and I'm happy to share our experience with you today. So the first thing to consider when approaching queries is how cacheable those queries can be. There are in the wild, in all the thousands of clusters we've seen over the years, there are repeating mistakes that people make, probably just because of not being aware of the things that the easy fixes and easy changes they can do to significantly improve those. And having queries cached by OpenSearch is probably one of the most low-hanging fruit and the easiest fix that one can do. Elasticsearch and OpenSearch will cache queries based on some internal decided criteria. So if a query is not so easy to run and is being run many times, it's going to be a candidate for caching. And then OpenSearch will choose to cache it. Now, if your query is not cacheable, meaning it has some heuristics that make it non-cacheable, or it could be cached but not reused, then all of that effort goes to nothing. So one of the things you want to know to make sure is that your queries are cacheable. One prime example is what I have here on the slide, is the timestamps that you often use to query that are not rounded up. So if you are writing your timestamp yourself, or use date math even, and you're not rounding those up or down, that would not be a cacheable query. That query is just going to run over and over again. Obviously, every time it's going to run, it will have a different timestamp attached to it, and that's why it's not going to be cacheable. So one very easy fix to make is to just take the timestamp and round it to the next even minute if you have so many queries, but usually we even recommend to round to the hour or even to the day. Usually it's fine, so you just query for more hours, and then if you need to filter that for exact periods, you can do that on client side, but at least you got it optimized against the cluster itself. For queries to actually be cacheable, so if the query is cacheable, but you don't run it under a filter context, that means that query is going to run and actually be computed for scores, for the result scoring that the relevance ranking that Elasticsearch and OpenSearch do out of the box. It will not be cached. So even if you made that change that I just mentioned, you still need to run that within the filter context. So a Boolean query and run it inside a filter instead of a must clause, and then it will be cached. So we mentioned rounding up timestamps, and just mentioning that explicitly, if you don't need scoring, don't run those queries under a must clause and just run them in the filter clause. A lot of queries will get cached and just let OpenSearch do its thing. Another very common mistake that we see is queries that use scripts. Now, script queries will actually create a full table scan query, and those will essentially be very expensive to run, but also not cacheable. So, and many of the scripts that we see can actually be easily translated to some sort of a field query. So instead of doing some computation in a script, you can change that logic to be a new field even on the data itself, and then it will be indexed and queryable and probably even cacheable. So this is one big mistake that we see. To know if you have queries that are applicable to those changes, there are a couple of ways. I'll discuss one of them in the end, but you definitely need to monitor on your cluster the query and request caches. You want to see how memory usage looks like and how the eviction rate looks like, and then you'll get a good understanding of how well you're doing. Another thing to note is that many queries are considered by OpenSearch as expensive queries. So expensive queries is a full category of many types of queries. So even if you cannot cache a query, but even if it is actually going to get cached, still some queries can run faster, and there's no reason to run them in a slower way. So I mentioned scripts. It's here again just because of how severe misuse of them is in the wild. So script queries will run full table scan, and there's usually a good way to avoid that. I would also mention the risk score query that sometimes can be used for places where heavy scripts or scoring algorithms needs to run. So that could be used to minimize the amount of work that you do, even if you have to do it. Another very common mistake that we see happening in the wild is using n-grams. So if you go on the web and try to do things, you'll get to many blog posts talking about n-grams. And the fact is that 95% of times you actually don't need to use n-grams. There is tons of ways to do what n-grams allow you to do in a more efficient way. So in most cases, when we see n-gram queries, those using n-grams is not necessary. And that will actually cause a very expensive queries to be run because of how n-grams are running. If you want to learn more about that and about the alternatives, I added a link here to a blog that discusses that in more length. Other expensive queries include wildcard queries, prefix queries, regex queries. So all of those are queries that essentially just don't use the inverted index as we could let the OpenSearch do it. They either bloat the query without you even noticing to be a very expensive query, or just skip the inverted index altogether. And again, many times there are ways to avoid that, but sometimes you don't. But again, there are ways around it. Every case has its own solution a lot of times. Another common, I wouldn't say mistake, but another cause of expensive queries is just the large result set that are returned. So asking for 10,000 results back, it's not very usable. So instead of asking for 10,000 results, ask yourself, do you need those 10,000 results? Because the customer in the front end is not really going to go through all of those 10,000 results. Alternatives would be using aggregations to demonstrate how those results are spread across, and then kind of how we can filter through them and drill down to the results. If this is for an automatic process, there are mechanisms for that. So scrolls and point in time in some cases, search after, which is more efficient, and so on. Another relatively new topic to OpenSearch is vector search. And there as well, there are some considerations of what's considered expensive and when you need it. So KNN, so exactly K nearest neighbors, is some sort of a brute force query. Again, there's no indexing involved and nothing of the sort by design. Sometimes it's actually the right way to go. So sometimes if you have, let's say, hundreds of thousands, maybe low millions, there's no reason for you to do anything else, and KNN would work just fine. But for very large data sets, it's going to be very compute intensive. And then you need to do right sizing to understand what you need to do. Because if you cannot use KNN, you will need to use ANN, and then you will be trade-offing performance CPU work with more memory and disk scans. So again, you need to understand the use case and then take it from there. I also attached a link to our blog here talking about expensive queries in more length, but essentially that's what is this explaining here. Okay, so you want to understand if you have slow queries and finding these slow queries and then profiling them and figuring out what to do. How are you going to go about that? The standard advice is to go and use slow logs. Slow logs will essentially log all the slow queries. So the usual, again, advice out there would be to enable slow logs in OpenSearch. On Amazon OpenSearch, it will be writing to S3. On self-managed, it will probably write to local disk. And then those slow logs will be written with some sort of a threshold. So Every query that runs above 500 milliseconds will be logged to the slow log. Now, the point is that I'll talk about that in a second, but that's probably not the smartest way to find your slow queries. And I'll touch on that in a second. Once you found the query that you know or assume is slow, you can use the profile API to understand what parts of the queries are slow. But like I mentioned, if you go and just log all queries that are slow, you're not necessarily going to find the queries that are the most interesting because of the following reason. A lot of times when you experience slow queries, what's slow is not the actual query, but is the cluster that is overloaded or has performance issues, or maybe a different query triggered some sort of eager loading of global ordinals, or just a lot of parallelism or concurrency with queries, and maybe the disk is very busy. So the performance of the cluster is just not as good as it could be. And then the slow log will just output all queries, or all queries that have run slow, not necessarily the actual queries causing that, or maybe the root cause is with the cluster performance and it being under provision. So I listed a couple of things that you should be looking at before actually going to chasing slow logs, finding slow queries. And just to mention a few, I added to the slide here a shard heat map that we usually produce to our customers that show whether there's an imbalance of shards, but not in terms of the size on disk or the number of shards per node. Those usually will be balanced okay, mostly shards per node, but actually in terms of search rate. So maybe there are some very hot shards got placed on the same node, and those are experiencing bad search performance, but it has nothing to do with the actual query. And things like memory pressure. Is your GC set up correctly? Do you have enough heap space? Are circuit breakers being tripped? Do you get search rejections because of those issues and not because the search is just too slow, and so on? So I would say first go and optimize or make sure there are no bottlenecks in your cluster, and then go and start survey what queries are slow. Now, my recommendation on that second step is actually to get all the queries, so slow log with a threshold of 0, get all of those queries, all the queries for a period of time that will get you enough traffic, so a couple of hours and hopefully a couple of dozen of thousands of queries, and then analyze them in an independent way. So the way that we do that, we use a platform that's called Pulse. Just 2 words about that. Pulse is our automated software, automated platform for observability, proactive monitoring, and a way to cut costs and improve performance of OpenSearch clusters deployed anywhere. And so we basically not just draw the graphs and send you alerts, but also give you the bottom line and estimate your health assessment and tell you the recommendations on what to do. And one of the key features of Pulse is query analytics. And query analytics will essentially allow you to stream those queries to you live. And so slow logs that are sent even live, but also offline is supported. And then we'll do that slice and dice. We'll analyze those queries, the latency, the size of the body of the query, the size of the response, query families, so fingerprinting queries to understand which queries are similar in structure, the same person or same type, the same part of the software created them, and then we'll get you the insight of, hey, this query does for example, cardinality aggregation, or has a very large size, and it correlates highly with the very high latency, and that's the query you need to optimize, versus, hey, look, the performance of the cluster is not good, optimize the cluster and queries will run faster. So that's what I have for today, and happy to answer in the Q&A section any questions about query analytics, query performance, and optimizing cluster in any way. Thank you.
Amazing. That was fantastic, Itamar. A quick note for all of you who have been asking, the webinar is being recorded and we'll be editing the video and sending it all out to you, so not to worry. In addition, we received multiple requests for slides, so we'll be sharing speaker slides from those speakers that are able to share them, so just stay tuned. Next, we have Kate Gavron, who's an OpenSearch expert and a senior cloud database architect at DoIT. Kate, I hear you have some great insights for us on node shard and storage calculations. We can't wait. The floor is yours.
Thank you, Maya. Let me just share my screen. Okay, yes, just a quick introduction. So first of all, thank you very much to Moa and Itamar for their insights so far. So my name is Kate Gavron, and I'm a senior cloud database architect at DoIT. So just a little bit of background really about DoIT and who we are. So at DoIT, we're an AWS premier tier partner, and our main role in our work with AWS is that we really want to help you simplify any of your cloud challenges that you have. We're really aiming to use different technologies and our platform to help you optimize your cloud. And we specifically focus on cost optimization and cost management across multi-cloud. To do that, we have a wide range of experts who work at DoIT to really enable you and to upskill you as well. So a lot of our role is to help you and also to teach you how to do things better yourself. So we're currently actually managing $1.7 billion of cloud spend across about just under 3,500 customers around the world. And we're currently saving our customers around $300 million every year based on what they'll be spending without our help. So just to go into some of the areas on OpenSearch. So one of the main things, if you've been using OpenSearch for a while, you'll already be aware around things like shards and nodes. So when you're doing your shard size, you really want to be sticking between the recommendation, somewhere between 10 to 50 gig for each individual shard. But there are some differences here in that actually, if you're running a search heavy workload, you want to be running between sort of like 10 to 30 gig. Whereas if you're running a write heavy workload, you want to be running 30 to 50. Now, the main reasons for this is if you think about how sharding works. So when you're doing a write, you need to go and write to every single shard. So if you have, say, 5 primary shards with replicas, you actually have 10 shards. So when you do a write, you have to write to 10 shards. When you're doing, if you're doing a read, you actually only need to read the same number of shards as you have primary shards. So again, if you have 5 primary, you only need to read from 5 shards. So effectively, you're reading from half the number of shards you would be when you're doing writes. So if you're doing a very write-heavy workload, you actually want to have fewer shards, which in general means you want them to be larger to start with to allow you to grow. You also want to make sure you start towards the bottom end of that. You don't want to put everything basically shards up to 50 gig to start with, because then you won't have anywhere to grow, and you will find that if you go over the 50 gig, that then your queries and your costs may well start to grow. It's really important as well that you start to work out your sort of optimal number of shards before you load that data. So you really want to make sure that you work it out. You can reshard, you can reindex after, but it typically causes downtime and it causes increased costs. So you want to work it out first. So first of all, you need to work out the amount of data that you're going to store. So if you want to store around, say, 100 gig of data, you want to make sure you've got a little bit of growth for your search-based workload, then you probably want to start at around 10 gig. And if you do that, then you're going to want to create maybe 10 shards. That 10 shards will allow you to grow to actually about 300 gig before you hit that sort of 30 gig limit, where you may start to see your query performance and your costs start to fall. In terms of the number of shards, you want to be running a maximum of around 25 shards per gig of memory on your node. So again, if you're likely going to have more than one index with multiple shards. So if you're running that, you can use that as a calculation to start to work out how many gig of memory you need, which then helps you to start planning how many nodes you need. If you're running self-hosted OpenSearch, then your indexing defaults is 1 primary and 1 replica. However, on AWS, you get 5 primaries and a replica set, so 10 shards in total. So that's a really key difference between self-hosted and AWS that you may need to be aware of, specifically if you're moving across to the AWS OpenSearch managed service. And if you just import your data, that you may see your costs change because you may suddenly now be storing more copies of your data, more shards. You can use like the cat and allocation API, basically to check like your shard usage. So you can actually double check where your shards are being stored, how much data is in each shard, and then you can start to use that as well as like testing, and then you can make changes based on that information. And a final really important point is around storage skew. So just to give an example. So in this example here, we've got 10 different shards being split across 4 data nodes. And you can see that that's not optimal because your data is not evenly spread. So some of your data nodes have got 3 shards, some have only got 2. And what you will likely find is the ones with 3 are going to be doing more work. So the ones with the 3 shards are going to be busy. You may actually be hitting CPU bottlenecks or memory bottlenecks, and the other 2 might be more idle, which means you're probably wasting CPU costs. So the best way, if you can do this, is to try to make sure that you keep your shards and your nodes in an equal ratio. So in this simple example, we have 6 shards and we have 6 data nodes. But if you are running 6 shards, the replica you want to make sure is that you maybe want to have 2 data nodes that would have 3 shards on each, or 3 data nodes, 2 shards on each. What you wouldn't want to do is say have 4 data nodes, because then you end up with some of the data nodes with 2 shards, some with 3. And then again, that's going to cause you bottlenecks and it won't be optimal. So the next thing to talk about nodes is about these specialized node roles. So really the node roles you can have different functions within your cluster. So some of these are things like a manager that does effectively the work. It makes sure that the queries get sent to the right place. You have your data nodes where your data is stored, your search, which is specifically around doing your queries. You have coordinating nodes. The coordinate nodes are only really useful in very large clusters where we're talking 10, 15 nodes or larger, when you really need to have a specific pool of resource just to make sure your nodes are working together in unison. And then you have 2 special types, ingest and dynamic or machine learning. So by default, all of your nodes can be a manager, a data, an ingest, and a coordinating node. But sometimes we see customers specifically on, just make this clear, this is only for people who are running self-hosted. On AWS, you are fixed with having your manager nodes and the other nodes basically being data, ingest, and coordinating together. But if you're running self-host, you can customize these roles on each individual node. But we're actually seeing quite a few customers who take this too far and who have individually identified nodes that have just an ingest node, just a search node, some data nodes. And you'll probably find that you just don't need that. There's been very few edge cases where you might need an ingest node, but we're typically talking customers with very high writes. And by very high writes, I mean you're effectively replacing or almost doubling your data ingest every single day. So whatever you've got saved, so if you've got 100 gig of data in there, you're also ingesting another 100 gig each day, or you're replacing it. So you might have logs, huge volumes of logs that are being ingested. If you have that, then you may find that your ingest is the bottleneck in your cluster, and at which point it may be better to create an ingest node so you can move that off, and then you can scale that node individually if you need. But again, the best thing to do is to try to keep everything standardized across your cluster until you reach those specific use cases where you need to make changes. And again, you can remove some of these, which actually helps to remove memory. If you're not running a machine learning workload, then you don't need to have the machine learning role. By removing that role, it actually frees up a small amount of memory and CPU that would otherwise be running the machine learning components, allowing that to then focus on what you are doing, your searches, your data ingestion. And again, you can use like the OpenSearch benchmark tools to test your configuration. You can do that on a subset of your data. You can run that and it'll show you where the bottlenecks are. You can then use that data to understand, is it worthwhile for you to have an ingest node, or do you need to have a specific search node depending on exactly what your workload is doing? So another important one, which again can really easily get missed, is around unused indexes. So quite often our needs change as an organization. something that we set up 5 years ago and probably isn't being used today as it was back then. But yet, how often do we actually go through and check, do I still need this? Are we still using this? Is my application still reliant on this functionality? And what you can find is that often with OpenSearch, you actually end up with indexes that just aren't being used. So by removing these, you can effectively find that you can improve your performance. If you're running fewer indexes, that's going to lead for like less overhead on your cluster. That's going to be really significant for your search and indexing operations. You're not going to have to write to so many different indexes when you do updates. You get a lot faster response times and a lot less competition for your resources. That's going to help you reduce your costs. If you're not saving that index, you're going to be saving storage space. You're also not going to need to maintain those, so you can save on CPU and memory as well. It's also going to make your life a lot easier in terms of your management. The fewer indexes you have to manage and worry about, and that's going to make life easier for the operations. It's going to make your backup processes easier. It's going to reduce your complexity. And again, things like upgrades will be much easier for you to do. Your settings, you won't have to adjust so many indexes if you make modifications. And ultimately, it's going to enhance your cluster stability. So each index, no matter how much of its size, requires a certain amount of overhead just to keep it up and running, just to maintain it. So the fewer indexes you're running, you're going to lessen that load on your manager nodes that are trying to keep everything in sync, on your coordinating nodes. And that in turn is going to free up some memory, some CPU back to your day-to-day operations. So on the side, you can see effectively like a command that you can run to get information on your indexes. And you can see the first one is a pretty standard index that's actually being used. And you can see, this is simplified, cut down. The actual query will give a lot more data. I've just focused on the bits you need. But what you're looking for is the search. And in there, you've got your query total and then your query time in milliseconds. Query total is number of queries and query time milliseconds is exactly as it states. So the top one, my index 1, it's a very typical index, 30,000 times that's been hit. Sorry, 10,000 times that's been hit. And the second one is one that's pretty much unused. It's only actually ever been queried 10 times in total. Now you may need it. It might be that those 10 queries run once a month as a job. I don't know, like a billing cycle that's required, but it probably isn't. So it may be worth at that point having a look to see whether that index can in fact be dropped. Could you make some small modifications to your application to no longer rely on it? And I just want to talk about sort of index management. So that follows on a bit about dropping the unused indexes first. But in index management, you've actually got 3 different options here. You can do index state management, which allows you to automate various tasks based on like the state of your index. So you can apply automated policies that sort of like manage the life cycle. So similar to what Moore was talking about, where you can move things into ultra warm storage or cold storage. You can use ISM to do things like automated rollovers, where effectively you roll over to a new index after a certain period of time, which means the indexes stay small. You don't end up having them being huge and oversized. You can actually automatically like delete indices that you don't longer need. So after a certain period of time, you could maybe delete all the data older than 60 days. Then we have options such as index rollups. So index rollups are typically used for time series data. And if you think about that, you're more likely to run detailed queries on the most recent data. The older data you might need for analysis or trend data, but you probably don't need such detailed metrics on the older data. So using rollups, you can aggregate and you can store your historical data in effectively like a wider or a coarser time bucket. So rather than it being kept second by second, you might put it into hourly data or daily, depending on what you need. The benefits of doing this is, again, you're going to reduce your storage costs. By aggregating your data into fewer records, you're going to significantly reduce the amount of storage that you need. You're also going to get improved query efficiency. Bearing in mind that most of your queries are likely to be on the more recent data, it means that actually you don't need to query the older data so often. So when you actually do run a query on that, it's more likely to be an aggregated type query or a trending query. And by having it rolled up gives you faster access to that. And then finally, you can do index transforms. So index transforms actually allow you to create a new index by transforming an existing one. So similar to maybe like a materialized view. So on these, you can basically, the benefits of these is you end up with sort of optimized data access. You can query that new index efficiently if you need to. And again, these new indexes tend to be smaller than their source indices. The fact that Maya's gone back on camera means I'm close on time. So I have just one more. And so specifically, how can Do It help you in this? As I mentioned right at the beginning, one of the main things that we work on in Do It is really helping customers understand their costs and really understanding how to cost optimize across their entire cloud platform. So one of the main things we have is area called anomaly detection. So anomaly detection is actually a machine learning driven tool based on your cloud data that enables you to very quickly see if something's gone wrong, if you have a sudden spike in your costs that's unexpected. So even if you would normally have a spike once a month for a billing cycle, it will take that into account and it will know what's normal. And it can understand, and you can get really fast, extremely quick information on when something's gone wrong. And in OpenSearch, this could be perhaps if your application has suddenly ingested a lot more data, or someone's run a query that's suboptimal, that's caused additional CPU load, which has caused things to spike and your cost to increase. So last year alone, we actually managed to save $196 million across our customers using this cost anomalies. So thank you very much for your time, and I will hand back to Maya.
Amazing. Thanks, Kate. That was so informative. Now we'll move on to the live Q&A section. So remember, now is your time to ask your questions to 3 amazing world-class OpenSearch experts. So please just specify to whom your question is addressed to. So we'll kick off. Our first 2 questions were from more. So the first question is from an anonymous person. He or she would like to know, you had M5 extra large instances on the diagram, but M6A would probably be even cheaper and more performant. So Moore, can you speak to that?
Yeah, sure. I'm guessing it's regarding the slide with the ultra warm sizing and pricing, the real life example. So the main purpose of this slide was to show the cost savings when you use data lifecycle management and not necessarily change CPUs. So I guess it's true what you said, but it wasn't the main purpose of the example.
Okay, great. Abby would like to know more. Is OR1 based off of x86 or Graviton, or can we use either?
Well, I don't know what it's based on. It's not public information. I believe it's based on Graviton, but it's not something you can choose. You simply choose the OR1 instance. That's the name of the instance.
Okay, amazing. The next question, I believe, is for Kate. So Kate, when talking about memory requirements, does it matter to size the JVM max memory on large installation? I read to not go over 32 gigabytes.
Yeah, I assume this is talking. Yes, you don't want to go over the 32 gig in terms of the JVM. It's effectively to do with how Java manages its memory requirements. So you'll end up getting stack issues if you do go over that. So yes, it does matter not to go over 32. You can go lower. Again, it's about being optimal. So it's about sort of like manage your cluster. So it's basically starting to look at your monitoring, looking at your statistics, and then understanding exactly how much memory you want to allocate for each part. So it's going to come down to your individual workload.
Amazing. And Kate, another question for you is from Ellie. He wants to know, is there any easy way to get a list of unused indexes?
Yeah, it was on the slide. So effectively, if you use the underscore stats API, and then you can actually run that with a JQ stats, a JQ parameter, and you can then get the indexes query. It was on the slide deck, which will come out to you.
Amazing. Arjuna has a question. I'm not sure who it's addressed to, so I'll read it and hopefully one of you will have the right answer. I have one question. How can you see what index is receiving write search queries? In old Elasticsearch / Kibana, I had a monitor view, but in OpenSearch, I cannot find a place where I can see load per index.
So I'll take this if I may. There is some monitoring. So Kate shared the API that will allow you to do it, but obviously it's a little bit troublesome, especially on large clusters, to just go through those. If you are on the managed service, there are some CloudWatch metrics that you can use to build those. I mentioned Pulse, are essentially our product, and what Pulse does is actually do exactly that. So just quickly sharing here, this is an OpenSearch cluster of some Acme organization. And as you can see, you can easily just go in and find the index patterns with just group indexes, but by index patterns automatically that are not receiving any writes or any searches. That will also demonstrate how to find unused indexes. So as you can see, slow logs are not, as this index pattern is essentially not used, and you can absolutely delete that. In the recommendation section, you will find a recommendation that tells you exactly how to do that. And then obviously you can just go and continue looking here on the HS logs and based on the search indexes, and you can see that this is the current one. Hopefully I answered the question.
Amazing. We have another question from Alexei. Not sure who it's geared towards, so we'll see. The shards math can be different for KNN or ANN indices. What is your experience? Then he also includes a passage below. So I'll open it up to one of our experts.
Yeah, I mentioned KNN. Kate and Moore, feel free to chime in to expand. This is correct. KNN is full table scan essentially. This is just brute force on all your shards, excluding pre-filtering if you've done any. And ANN works a little bit differently because there is some indexing involved depending on which approach you're going. So yeah, but it will, I would say it would translate to a similar approach to like you would have been using indexes, just the ANN indexes work a little bit differently.
Amazing. And before I address Abby's question, a reminder, we have another 5 minutes for Q&A, so don't be shy. You have three really amazing experts here to answer all your OpenSearch questions. So Abby would like to know, is it possible to make re-indexing much faster? Usually it takes too long to finish such a step.
I can take it.
Great.
Okay. So yes, reindexing, there are a lot of advice that I can give. It really depends on what you do. We just recently completed a migration from an Elasticsearch cluster running on a new version, so 8 point something, to OpenSearch, which as you probably know, it's not compatible, so we cannot use snapshot and restore. And then what we did, we had to use the reindexing approach, and that was even inter-cluster, so between two different clusters. So what we did, we essentially on the target cluster, sorry, we used 0 replicas. This is one of the items in the checklist. So without replicas, indexing will be faster on the target index. And on our specific use case, we deployed the clusters with local ephemeral disks. So again, it was different cluster. We could have done that. And then we also played a little bit with parallelism and used, in this case, Logstash with insane amount of parallelism to actually get that done. So we moved a couple of, I think, tens of terabytes in just a matter of a few hours, about 8 hours, something like that. If you're reindexing within the same cluster, then optimizing mappings, reducing replicas to 0, and looking at disk performance would probably be my best advice.
Amazing. Last call for any more questions. Again, you have 3 experts. We have another question from Roman. He wants to know, is there any guide to help with decisions for how to use ultra warm storage?
Mo, that's yours.
I don't have anything up my sleeve right now.
So what we've been seeing is okay, we have a couple of minutes. What we've been seeing is that ultra warm is specifically targeted at write only indices. So essentially, no updates, no deletes. So that would be more relevant to the logs and metrics scenario versus others. And then less frequently used as time goes by. So assuming you have a lot of data coming in, you'd move them to ultra warm, you'll be querying them less, so performance will drop and you don't care too much. And then again, you never need to update data there, so it's on ultra warm.
Amazing. And our last question is from Arjuna. What is your common procedure that you use normally when you feel and see that your cluster is overloaded?
I think it's going to be dependent. First thing, obviously, is to make sure your monitoring is working. You know, if you haven't got monitoring in place before you start and you don't know where to look, then, you know, how are you even going to know it's overloaded? So I presume if I'm overloaded, I guess actually the first thing I'd do is, it's going to sound weird, but do I care it's overloaded? Like, are my queries, am I actually being impacted? Is my customer, my application being impacted? Because we get this a lot, and people say, in my opinion, the most optimized database is one that's running at 100% CPU without a customer complaining. And that's the really important point. So it goes back to that business understanding of, you know, ultimately the business understanding of, is anybody impacted? That's the first thing. If they're not, carry on. It just means you're optimal. If you are being impacted, then it really does come down to analyzing exactly what's going on. If it's a sudden spike, it's likely to be query related. So then you need to have a look at your running queries. You can use some of the techniques that Tamar was talking about looking at like, what is your queries that are running right now that's causing your spike? If it's been gradual, an increase rather than a spike, it's likely that you're just putting more workload through your cluster. So it's now much more important to understand, what is your cluster doing? You probably need to scale it. You're probably hitting some bottleneck in terms of the available resources that's around. So that's like the main things you want to check. What's causing it to be overloaded? And then if it's query related, yep, you need to go and have a look at which query it is, start to tune that. If it's cluster, like you're just gradually increasing how much you're using your cluster, then you do need to start looking at, is it time to get specific nodes? Do you need to increase the number of data nodes? You know, do you need to increase your CPU? Do you need to scale out your cluster?
Amazing. Thank you so much, Kate. What a fantastic session. Remember, optimizing your OpenSearch deployment is an ongoing process. By applying the strategies you learned today, you can unlock both cost savings and performance improvements. If you'd like to explore further, stay tuned. We'll be sending out a follow-up email from us with a link to the recording and any slides that are available. And thank you again to our speakers, to Big Data Boutique, Do It, and AWS, and for all of you for attending. Have a wonderful day. Bye, guys.